This topic we will talk about silicon carbide MPS. This is our new product. It will release next year, Q1. The agenda we will begin from silicon carbide MPS introduction. And because silicon carbide is new generation semiconductor materials, we will take it to compare with silicon-based product FRED to see what is the difference. And I will take the silicon carbide MPS to compare with other competitors in the system board PFC. Before that, I would like to introduce you what is PF and why we need to use PFC. And I will use the software to illustrate how does this PFC operation and the evolution. The first is silicon carbide MPS. Compared with traditional silicon-based, silicon carbide material die has 5 superiorities. The first superiority is silicon carbide band gap is 3 times than silicon-based products. The second benefit is silicon carbide breakdown field is 10 times than silicon-based die. So by the same voltage spec products, silicon carbide die thickness is only 33% of the silicon-based die. And the third superiority is silicon carbide is thermal conductivity 3 times than silicon-based die. And the fourth superiority is silicon-based meeting point is 3 times than silicon-based die. So silicon carbide has better thermal dissipation effect. It could operate in high temperature and high frequency environment. As the fifth superiority is silicon carbide, its recovery performance is better than silicon-based products. This is a silicon-based products. When we apply forward bias to become reverse bias, there are 2 portions need to be discussed of their reverse recoveries. The first portion is this hose in the N- layer. It needs to be swept back to the P layer. Another portion is electrons in this N- layer. It needs to be swept back to the N layer. So that's the reason the recovery time is long. Now silicon carbide is shaky. In forward bias to apply reverse bias, there are only 1 portion needs to be discussed. The electron in this N- layer, it will need to be swept back to the N layer. That's the reason the recovery time is short. And the TSC, silicon carbide shaky, we adapt the latest technology, MPS, the merge pin in shaky. This is a silicon carbide shaky die structure. We will add in P-wire here. It has 2 benefits. The first benefit in forward bias, this can increase maximum forward surge capabilities. Second benefit in reverse bias, this can reduce the leakage current. And the silicon carbide is a new generation semiconductor material we take to compare with silicon-based FRED. The comparison group, the first will take silicon carbide MPS, and we will take TSC FRED, the spec 600 volt 8 ampere, and the B-shapes FRED. So the reverse behavior like these pictures. The green line is the B-shape FRED reverse behavior, and the blue line is the TSC FRED reverse recovery behavior. The red line is TSC silicon carbide MPS. So the silicon carbide MPS is IRM and TRR are much lower than the silicon-based FREDs. It demands the silicon carbide MPS QRR performance is only 33% of silicon-based FRED. It means silicon carbide MPS has lower reverse recovery loss. And we apply different forward current to see what is the comparison result. This is TSC FRED. When we apply forward current, as like this green line, we got his reverse recoveries. When we increase forward current to 4 ampere, it's blue line, and 8 ampere is a red line. So when we increase the forward current, the IRM and TRR are increasing significantly. Even B-shape have this FRED have this same phenomenon. But silicon carbide MPS, when we apply the forward current from 2 ampere, 4 ampere, and 8 ampere, the IRN and the TRR almost the same, no change. So silicon-based FRED, the IRN and TRR are affected significantly by this different forward current. But silicon carbide MPS is almost completely unaffected by this different forward current. And we will apply different temperature. Let's see the results. This is the FRED, silicon-based TSC FRED. The room temperature is the red line. When we increase the temperature to 100 degrees C, we got reverse recovery like this blue line. So the RN and TR are significantly increasing. Even beside FRED, it's become worse. But the silicon carbide MPS, from room temperature to high temperature, its RN and TR keep the same, very stable. So silicon-based FRED, their RN and TRR will be affected significantly by these different temperatures. However, silicon carbide MPS, RN and TRR has no temperature dependency. So we will take silicon carbide MPS to compare with other competitors in the system board PFC. Before that, I would like to introduce you what is the power factor. To discuss power factor, it has two conditions. The first condition, when the loading is linear, the input current is sinusoidal waveform. If the loading is a resistance, when we apply input voltage like this blue line, we'll get the input current like this red line. The current and the voltage are in the same phase. It means the energy from the power source is 100% consumed by this loading. If we put the inductor here, and we apply the input voltage like this blue line, we'll get the input current like this red line. So the current will delay the voltage phase to green, like this portion. When the voltage is positive, but current is negative, it means some energy from power source will be stored by this loading, and it will release back to the power source. So the power will not 100% consumed by the loading. If we replace a capacitor here, when we input the voltage waveform like this blue line, we'll get the input current waveform like this red line. So the voltage will delay the current phase to green, like this portion. When the voltage is negative, but current is positive, it means that some energy from the power source it will be stored by this capacitors, and it will feed back to the power source. The energy will not be 100% consumed by the loading. To describe this relationship, we use this. Apparent power, it means how many energy from your power stations. The unit is voltage ampere. It will equals the real power. It means how many energy your loading actually consumed. The unit is watt. Plus the reactive power. It means the energy was stored by this circuit, and it will feed back to the power source. It will not be 100% consumed by this loading. The unit is VAR. So there's the index power factor. The PF will equals the real power, how many energy your loading actually consumed, divided the apparent power, how many energy from your power source supply. It will equals a cosine theta. The power factor between 0 and 1, if power factor is good, it is 1. It means the voltage and current in the same phase. Like resistance, the energy will 100% consumed by this loading. If the power factor is bad, it's less than 1, like an inductive load or capacitive load, it means our energy will not be 100% consumed by loading. It will be storage in this loading, and it will feed back to the power source. For example, if loading will actually need 1 kW, the real power, how many power stations need to be supplied? The case 1, if the system, the power factor is good, it is 1. The power station will need 1 kW divided to 1 is 1 k voltage ampere comparison power. The capacitor, if the circuit power factor is bad, it's only 0.5. It will need power supply 1 kW divided 0.5 is 2K voltampere. It's double. So increase the power factor, we have benefit. Input appliance power could reduce, power station provide lower power, so the carbon could reduce. It help reduce power loss when we transmit these energies. The second condition, if the loading is nonlinear, so the input waveform is not a sinusoidal waveform. Like this circuit, the bridge and the loading is a capacitor and the resistance. When we input the voltage waveform like this green line, we got an input current line like this yellow line. So this current waveform is distortion. It's not sinusoidal. It contains many harmonic waveforms. So not only we need to consider if the voltage and the current is the same phase, as we had talked about previous slide, we also need to consider this phenomena. We use another index, Fin, THD, total harmonic distortion. Finally, we got the power factor equals 1 divided square root 1 plus THD squared and cosine theta. How to calculate this formula? There's two maths from physical consideration. If you want to clearly mathematical calculation, you can use math 2. It's from voltage waveform add in THD consideration, and after some calculation mathematically, finally we got the power factor equals 1 divided square root 1 plus THD squared cosine theta. So we know to improve power factor is important. We'll use field FC to do it, the power factor calculation. There is a criteria EN61000-3-2. It recommends add in PFC if the switching power bigger than 75 watts. Take example, this is AC-DC rectifier, but there is no PFC. When we input the voltage current, we got this input distortion current. So the power factor is very bad. It's only 0.56. If we add in PFC here, when we input the voltage current, we got the input current like waveform like this red one, yellow one. So not only the current and voltage in the same phase, but also the current waveform is like a sinusoidal. So the power factor is close 1. The PFC control scheme like this, there are two portions. The first portion is this external voltage loop. The output voltage will compare with reference voltage and provide the current signal. This will times the input voltages and make the current and the voltage in the same phase. Another portion is external current loop. This current signal will compare with the inductor current, and it provides the PWM duty cycle to control the MOSFET. So, in order to let you know clearly how does the PFC operation, I will use a software to illustrate to let you know how does it work and the evolution of the PFC. This is a PFC software simulation. We use a bridge here, and the loading is capacitor and the resistance. There is no PFC. When we input the voltage like this green line, we got the input current waveform like this red line. So this current waveform is distortion. This is not sinusoidal waveform. The power factor is very bad. It's only 0.52. How to improve it? Based on this circuit, we add an inductor here. When we apply the input voltage waveform like this green line, we got the input current waveform like this, the pink line. So the pulse width become more broader. That max is the power factor improving from 0.52 to 0.72. We still can do further improving. Based on this circuit, we add in another capacitor here. When we input the voltage waveform, the green line, we got the input current waveform, another green line. So compared with previous current waveform, this current waveform first is more broader and is shaped a little bit like sinusoidal waveform. It can improve in the power factor from 0.72 to become 0.81. But we still not satisfied. We still can do further improvement. Based on the circuit, I add in a switch and make the switching frequency 1 kHz and put another diode here to make this circuit like a boost topologies. So when we increase in input, the voltage waveform like this green line, we got input current waveform like this yellow line. So this current compared with the previous current waveform, the pulse width more broader and the shape is like a sinusoidal waveform. So it improving the power factor from 0.81 to become 0.88. So what if I speed up this switching frequency? We got the input current with like this yellow line. It become more smooth, so keep the power factor the same. And based on this, we can suppress the current trace from previous 55 mA, suppress it to 45 mA. And based on this benefit, I can reduce inductor size. We can reduce the 50 mHz to 5 mHz, and we got this input current waveform. It still keep the same. The cycle sinusoidal waveform and the broader, so keep the power factor the same. That's the reason when we increase the frequency, we can reduce and shrink the capacitive component size. So finally, based on this circuit, we add another two portions, external voltage loop and internal current loop, like we have talked about previous. So we add in the external voltage loop, we can sense out the voltage of the voltage signals, and the internal current loop, we can sense out inductor current signal like this. So we use a controller to control the PWM duty cycle to operate. We've got the input current waveform like this yellow line. This is a very completely very beautiful sinusoidal waveform, and the current and the voltage in the same phase. We magnify it, we can detail to understand how does the PWM switch it to make the current to follow the voltage waveform. So we take our silicon carbide MPS to compare with other competitors in the system board PFC. The comparison group, TSC, we take the Gen 1 silicon carbide MPS, and Bichet is Gen 3, Green is Gen 6, Infineon Gen 6, onsemi, and ST. And we compare the device, the diode performance we add first. The room temperature, Infineon got the lowest, so he has the best performance, is ranking 1. The next is TSC. The next is ST, and the wings Green, Bichet, onsemi is the last. So if we ramp up the temperature to 125 degrees C, the Infineon superiority will reduce when this temperature rises from ranking 1 to be ranking 5, but TSC keep a very the same, ranking 3. And we compare the device reverse performance, the QRR. Infineon got the lowest QR, so its performance is ranking 1. The next is onsemi, the next Bichet, and ST Green TSC are very close. If we take these two index, we add QRR, we use a form to describe the device performance. Infineon got the best form. The next onsemi, the next Bichet, ST Green TSC are very close. And we take these 6 samples to test the PFC system board at 106 watts. The first condition, we input the voltage is 115. We apply the load is 10%, 20%, half percent, and full loadings. And we use 80 plus titanium criteria to examine if they satisfy or not. we got the power efficiency like this. Infineon have the best power efficiency, and the other 5 TSC, Bichet, Green, Onsemi, ST are very close. So all the parts comply with the 80 plus titanium standards, and the Infineon got the best power efficiency, and the other 5 samples are very close. And because Infineon his power efficiency is the best, so he got the lowest the diode cast temperatures, and other 5 samples are very similar. And we also record their system board reverse recovery waveform like these 6 pictures. We superimpose to become this to compare the TRR almost the same, only the IRN a little bit difference. Based on this information, we calculate out the QR performance. Infineon got the best QR performance, ranking 1. Onsemi is 2nd, Bichet 3rd, TSC is 4th, and next ST, the next is Green. The second condition, we apply higher temperature, 230 volt, and we use the rated roll is 10%, 20%, half roll, and full roll, and we apply the 80 plus titanium criteria to examine if they satisfy or not. So the power efficiency Infineon got the best. The other 5 group, TSC, Green, Bichet, Onsemi, ST, are very similar. So all these parts comply with these 80 plus titanium criteria standards, and the Infineon have the best power efficiency. Other 5 are very close. And because Infineon got the best power efficiency, so his diode cut temperature is the lowest, and other 5 are very similar. We also record their waveform behavior in the system board, and we can superimpose to comparison. TRR are very close, only the IRN a little bit difference. And we calculate out the QR performance. Infineon got the best performance of the QR. Onsemi 2nd, Bichet 3rd, TSC is 4th, it wins ST, the left is Green. So, summary, silicon carbide products, thermal dissipate effect, reverse recovery are much better than silicon-based products. And we, TSC, silicon carbide, Shaki, we adapt latest technology MPS. It has 2 benefits. The first benefit is the in forward bias, this can increase the maximum forward surge capability. As in reverse bias, this can reduce leakage curve. And we take these 6 samples, include the competitor, to test in the 806 watt SiC MPS system board. Infineon power efficiency is the best. And other 5 samples, TSC, Bichet, Green, ST, Onsemi, are very similar. This is all. Thank you.